Hello, this is Sijie. I will introduce our work on positive-congruent training. Consider a deep image classification model. On a set of images, it will make correct and wrong predictions. The quality of this model is well captured by the average error rate. Now, imagine this model gets deployed into a real-world application. At a later time, we replace it with a new model that has a lower average error rate. After this model upgrade, you may actually see some images become incorrectly classified, even though these samples were fine before the upgrade. This makes the upgrade seem backward. This behavior means the independently learned new model is introducing new errors that the old model does not. We call these cases negative leaps. We can further measure the proportion of negative leaps in a set of testing images and calculate the negative leap rate, or NFR for short. These negative leaps can nullify the benefit of the model upgrades by deteriorating user experience or breaking post-processing pipelines. As the result, models are seldom updated despite the steady stream of improvements reported in the literature. In this work, we study the method to avoid negative leaps in model upgrades, which is problem of positive-congruent training. Negative leaps are widely present between model trained with modern deep CNN architectures. On ImageNet, changing model architecture from ShuffleNet to Inception model leads to 9.3% NFR, but bring only 0.17% accuracy gain. Deepening the ResNet architecture from 50 layers to 152 layers leads to 4.8% negative leap rate. And increasing the training data from 50% of ImageNet to 100% on ResNet 18, we get an NFR of 3.8%. These cases with lowered average error rates are all leading to non-negligible amounts of negative leaps. This is also true when we go from an earliest AlexNet model to a large ResNet 152 model. When we train multiple models with the mere difference in initialization, the NFR will still be significant. This suggests that, first, simply reducing error rate is not sufficient in avoiding negative leaps, unless the error rate drops to zero. Second, when the models travel along the equal error rate ring, they are trading errors. This means even at the same error rate, it's possible to find a set of model weights that leads to a low NFR to the old model without sacrificing the error rate. This observation suggests that positive-congruent training is worth to investigate. For the case where the old model is already given, we propose to use focal distillation to achieve PC training based on knowledge distillation. Focal distillation adds additional weights to training samples on which the old model is correct. In this way, it forces the new model to follow the old model only when it's correct. For the future proving case, where the reference model needs to be selected to ensure the best chance of future models to have lower NFR. We found that using ensemble trained with different initialization as both the reference and the new model leads to low NFR. Even more interestingly, the NFR decreases when the ensemble becomes larger and larger. This is also true when the two ensembles have different architectures. We tested these approaches on cases of model upgrades involving either architecture changes or training data growth. Results of our method were denoted as blue. They can effectively reduce negative leap rate. Now, we have scratched the surface of the problem of positive-congruent training. A lot is still waiting to be uncovered for this fascinating but also highly industry-related problem.